Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. Welcome to the public doctoral defense of Mark Daniel Alea. I declare the session open. Ik heet u van harte welkom op de openbare doctoraatsverdediging van Mark Daniel Alea en verklaar de zitting voor geopend. Mark Daniel Alea behaalde de Master of Science in Electrical Engineering aan de University of the Philippines, in de Filipijnen. En hij heeft aan de faculteit Ingenieurswetenschappen een proefschrift voorgelegd met als titel Chips die voelen. Volledig geïntegreerde bio-geïnspireerde elektronische huidsystemen. En dit tot het verkrijgen van de graad van dokter in de ingenieurswetenschappen. Hij behaalde, so Mr. Mark Daniel Alea obtained the Master of Science Electrical Engineering at the University of the Philippines. And he has submitted the thesis to the Faculty of Engineering Science that is entitled Chips That Feel, Fully Integrated Bio-inspired Electronic Skin Systems. And this is part of the requirements for the degree of Doctor of Engineering Science, and he will now proceed to defend his thesis. Mark, I just explained who you are and why we are here, and now you have the time, about 45 minutes, to explain about your work. After that, there will be the occasion to ask questions from the jury members, and there are more than are visible here. But there can also be questions from the public, but that's for later. For the moment, you have the floor.
Thank you. Just before we start, Professors Bartolotti and Caboli, can you hear me properly?
You need to take the microphone.
All right, I'm gonna
Take the microphone. Take the headset, that works.
I think I'll
Okay.
settle this. Chiara, can you hear me? All right, okay. Yeah, I'm happy to share my work in electronic skin systems. Basically, what kept me busy during, I don't know, the last 5.5 years of my life. I'm happy to see it through the end. This work is under the supervision of Professor George Hilland, and I'm happy to thank the jury for the constructive criticism and making the dissertation better. Let's just get on with it so we can all eat at the reception. So the outline of the presentation actually just follows the title itself. Easy. We start first with electronic skin systems. I describe what these things are, what are they useful for, and what are the challenges in building such systems. Then we go into our methodology of first leveraging integration to address some of the critical bottlenecks in this field, followed by our attempt to sprinkle in little bio-inspired concepts in the design into eventually implementing electronic skin systems that resemble more human-like in terms of the sensing. Throughout the presentation, I'm going to refer to electronic skins in sort of different ways. Electronic skin is skin, tactile sensing. For the purpose of this presentation, they're all equivalent, so don't be confused. What better way to introduce the topic than to, of course, name drop AI? Because apparently in 2026, we're all legally required to mention AI to make the presentation cool and sexy. But you know, I have amazing numbers for you. $109 billion of investments in AI in 2024. ChatGPT is so mainstream. It has 700 million weekly users, generating around 2.5 billion queries per day. That translates to 29,000 queries per second. Very amazing numbers. It certainly is. AI systems are transitioned from research labs into now mainstream, daily life of everyone. And it's not a surprise that these systems, especially in their early days, were inspired from biological systems, or they were bio-inspired. If you want to build intelligence, of course, you want to look at the most intelligent thing in the world, in the room. which is the brain. Also in the word, technically. So like I said, modern AI is bio-inspired or neuromorphic. Neuromorphic is just a fancy way of saying we're building hardware or algorithms that are inspired by biological systems. In biological systems, we have these things called the neurons, which eventually inspired the invention of these things called the perceptron. Turns out, these things are super simple. They're basically doing summation of multiple inputs, and you assign certain weights on these inputs, and then you apply it into a fancy function and you get the output. You train all these simple units and expand it to like, I don't know, billions of these, and it turns out you can get super complex behavior from that, which is exactly what you see in modern AI systems, and more especially what you see in biological systems. Again, AI is amazing, but it has its limitations. So, what we have been referring to AI is, a glorified language model. So it's very good at predicting language, predicting what is the next word in a sentence, or for a video, what is the next frame for this video. But it only predicts what looks likely, what not must be physically consistent. It doesn't have the real intuitive understanding of physics as biological beings do. And it sort of makes sense because these models are largely, stuck in some big building somewhere with no embodiment, or they have no body. So they don't experience reality as we do, biological beings. But when I say that these systems are largely in a dark room somewhere, turns out some of them are actually walking amongst us. In fact, I'm going to show you a video, and we can see when these intelligences escape the dark room somewhere, we can see their weaknesses become more apparent. I'm going to show you a video to prove my point.
Nothing beats a Jet 2 holiday.
Okay, I think we're quite getting the point here, right? So, like I said, intelligence generally have a limited understanding of the physical world, and that's especially true for humanoid robots. They're very good on small demos with strict set of pre-planned actions. But as soon as you introduce a small deviation, say the floor is a little bit slippier than expected, turns into a disaster. This is a classic case of the Moravec paradox, wherein what's easy for AI systems, solving your calculus homework, writing you a love letter, it's difficult for most human beings. But what's easy for human beings, walking straight without falling, lifting an object, is quite hard for most AI systems. And what went wrong there? Like I said, reality is complex. Perhaps we need the good sensors to capture that. A good analogy here is most modern AI systems are very good brains, floating in a water somewhere with no real sensors to interpret the real world, so they have no perception. perhaps we want to improve this other side as well, which is the neuromorphic sensing side. And it's not like people are not working in this field. In fact, eSkin's older, more successful cousin, the neuromorphic vision, has been doing a lot of the heavy lifting. In fact, it works on a simple observation of nature, or particularly the retina and the eyes, that perhaps not all pixels are important. On and off ganglion cells in the retina only respond when the change in the illumination or light happens. This is quite encapsulated in the example I have here. The one in the middle is a standard output of a camera, standard camera. The one to the right is the output of an event camera. What can you see here? So we see standard cameras are typically pretty slow. They have to sample the entire visual scene. It takes a lot of time. They have to process it. So normally you're quite limited with the speed. Therefore, you cannot capture all the little details of the wings moving. Whereas for neuromorphic vision, they can sort of focus all their bandwidth only on the relevant changes, which for this case are the movement of the wing. And by that you can finally capture the dynamics of the movement. Also, you can discard all the redundant data that perhaps might not be useful for you anyway, such as the white wall in the background. So it turns out vision is perhaps very useful for these systems, but we're human beings, we don't have eyes everywhere, right? So perhaps there's this other sensing modality that we need. In this next video, I'm gonna show you experiments they performed using robotic hands while grasping objects. So first, they only use vision, and next they use both vision and tactile perception. This tactile perception is just a fancy way of putting, the same behavior of what our skins are doing.
Let's look at some comparison videos. With tactile feedback, the robot can keep retrying to grasp the egg, even when a human resets the egg during grasping. However, a policy without tactile input may proceed to the next stage despite a grasping failure. When grasping grapes from the bag, the robot may pick up multiple grapes. Our visuotactile representation implicitly helps the robot to safely grasp with the appropriate amount of force, while the baseline policy may crush the grapes if multiple grapes are grasped.
I think that's a good point to stop there. So
let's look at some comparison
I told you
videos.
to stop. Okay, so
Let's look at some comparison videos.
see, there.
See, let's look at some comparison videos. See, let's
Okay. So main takeaways there are
let's look at some comparison videos. Let's look at some comparison videos. With tactile feedback,
okay. See, they're stupid. So I think the key takeaway there is you need both vision and tactile. In the case of handling grapes, they cannot regulate the grasp force properly, ending up crushing the grapes. Maybe good if you want to make wine, but not for general applications. And they tend to be very clumsy. Turns out, not only AI systems or artificial intelligence would benefit from this, but also us human beings as well.
robot.
So, in this next example, people put the sort of the same thing, tactile perception, on this time on neuroprosthetic hands. So you can see from the video how that actually improves a lot the experience for the user.
When you have a prosthesis, the only way you can know what you're doing is by looking at it. You can't feel that. You would know if you touch something cold, whether you're looking at it or not. Well, you can't do that with a prosthesis. You don't know if you're touching something at all, much less if it's cold or hot. And so we now have the ability to put sensors into a hand, and that can be fed back into these motors that give that sensation to that spot. So I have motors, I have a spot that feels like my index finger. Well, that's that sensor that's fed back, and that's where that particular motor gives that sensation. So it really gives that sense of feedback of, wow, I'm actually touching something, and I know that. And we've got a long way to come in this. It's certainly, we're still in the research phase, but the idea that we even have the opportunity to give somebody that feedback is really, really great. And it's really, it's taken a few years, but it will get there, and it's really great to be part of. When I put on my mascara and you go to close the lid, you know when you're done closing the lid because you can feel the tube start to turn, and then you're finished. I didn't know that before. So when I was using, it was great that I even had a prosthesis that I could use to do that, but I would just keep turning because I didn't know when I was finished. Well, now I can feel that. As soon as I start, my sensors will feel that bottle start to turn, and I know that I'm finished. It's just really simple, small things that don't sound like a big deal, really are. I can know if I'm holding something and I'm starting to slip, and it's starting to slip away. Or I can know if I'm shaking somebody's hand. I can know if I'm squeezing their hand too hard. That was something I never knew before. I just knew I could only tell by looking. So those are little small things that really make a difference in someone's life.
So what are the key takeaways here? Again, first, vision is not enough. By putting in the tactile perception, you open up this new world of object properties that you can then sense. Then it also improves interaction with fellow human beings. I think you know by now what I'm getting at. E-skin, or tactile sensor, basically is the artificial equivalent of biological skins. And we saw from the two examples that putting in e-skin is better than putting nothing at all. But current e-skin systems are very far from human capabilities. It's not a simple keypad that you only know where the touch is coming from. It's much more complex than that. If you want to build complex systems, perhaps we want to understand it first. So in the human skin system, there are 4 major mechanoreceptors. Mechanoreceptors are just sensors basically that convert the tactile stimuli into a bunch of electrical signals. These mechanoreceptors have varying sensitivities. Some are more sensitive to vibration, some are more sensitive to stretching, shear forces, but the key here is they're all converting tactile signals into spikes or action potentials. They don't fire very often, these spikes, so it's some form of temporal compression you're getting with there. And now the pattern and the rate of these spikes now carries your information. These action potentials travel all the way up to the spinal cord for second order processing before they go into the brain. I'm going to try to convince you that the intelligence in Tesla can be seen in our puny little fingertips. I'm going to start with the simplification. Let's imagine there is a 2D array of Merkle cells in your fingertips with very fine 400 microns of spacing, and some of them are connected into heminodes, or for our purposes, let's just call it a neuron. And not all of them are connected, so this creates something like a selective spatial sensitivity. So the neuron that connects to, say for example, the red here, only responds when the red sensors are in contact. For the blue one, when the blue sensors are in contact. Just by this simple mechanism, in our puny little fingertips, they form complex receptive fields. So, complex receptive fields is a region in your fingertip wherein there is varying level of sensitivity. Those areas in red are very sensitive. Those areas in blue are quite not. So imagine, a black bar that's scanning on the receptive field. And if it is in contact with the sensitive zones, you would expect the neuron to fire. For the blue zones, it will stay quiet. That's exactly what neuroscientists observe. In fact, this simple mechanism allows or improves the tactile encoding in such a way that when you change the input, the outputs are vastly different from each other. So you're basically improving the discriminability of the firing output with each other, in turn helping you with the tactile stimuli encoding. Another cool aspect of human skin sensing is when you're trying to detect slip. Our fingertips are very compliant, so when you're touching an object and it starts to slip, it will deform. This deformity results in very high spatial resolution strain field. And subtle differences in this strain field actually encode friction or slip. That's what neuroscientists believe at the moment. And this suggests that we need very high spatial resolution multi-axial force sensing just to detect slip. Multi-axial force sensing is just a fancy way that you're measuring all bunches of forces, normal, lateral, and whatever, rotational. But are current e-skin hardware equipped to do this? The short answer is no. Most of these systems, unfortunately, are ad hoc systems. They have low spatial resolution. And a key thing that maybe people overlook is this problem of you have to wire the sensor to your electronics, which is, a problem maybe not most people consider, because that's going to be prone to mechanical robustness issues because they can be damaged. Then the question is, can we leverage the same technology that has fueled the massive growth in the neuromorphic computing aspect, this time for neuromorphic sensing? And this technology here is called VLSI, or integrated circuits, integrated solutions, whatever. In a typical electronic circuit, you basically need three things: a capacitor, a resistor, and a transistor. And the main idea for integrated solutions is you try to make everything smaller, fit it in a very small package, like this. And it turns out this process of making the transistor smaller has been ongoing for how many decades now? So they have this observation that every 2 years the transistor density doubles, which is neatly encompassed in this thing called Moore's law. By this, you get circuits that are smaller, cheaper, you can add more functionality, and you can get, in general, higher performance. Then, where can we leverage exactly this technology for e-skins? Perhaps we can leverage the thing that makes stuff smaller to achieve higher spatial resolution. Perhaps we can build more power-efficient systems. We can solve the wiring problem I just showed you. And we can put more intelligence at the edge. In summary, the goal of this research is to bridge the gap between existing e-skin technologies and the remarkable capabilities of human tactile perception, in terms of the things I just mentioned you. This is a good point to disassociate mentally. It's going to be a little bit more complex for the next slides. See you mentally at the reception. We go to our methodology first, our bio-inspired methodology. Our bio-inspired approach is not blindly copying biology. We adopted a pick and choose strategy. We're just going to pick concepts or ideas from biology that are actually helpful. We also follow an end-to-end coherent design approach. Because we have complete control from the sensors to the readout to the processing, we can sort of co-optimize everything together. One aspect of bio-inspiration we adopted is this thing called per-taxal readout. This is the sort of thing you see in most primary afferents, like the retina I just mentioned earlier. So you're combining the temporal sampling of the neuron Now with the spatial compression of making everything connected one-to-one. However, this scheme imposes severe area and power constraints, and you have to miniaturize and integrate your tactile sensors on substrates that can actually perform the complex processing and the high density readout you need, such as CMOS and thin film. We're going to discuss that a little bit later. Turns out there is a good solution to this problem, this thing called level crossing ADC. First, it's inherently event-based. So that works pretty well because spike encoding is also the same thing. It's sampling asynchronously. It turns out it also has a very simple architecture. If you pick nicely, you can choose something that only needs two comparators and a way to reset the input. So you need this enables you to have a low chip area and power consumption, exactly addressing the issues I just mentioned. So, like neurons, LC-ADCs are very good for sparse input, which happens a lot with tactile stimuli. So, a comparison here, the one to the left is the behavior of a frame-based ADC. So, it's continuously sampling the input, even though in this part, there's really nothing happening there. So, you're basically sending redundant frames. So, whereas for LC-ADC, you're only sort of focusing everything on the meaningful parts of the signal. For example, there, the rising part. So you can sort of focus all your power in that small time instance. So what's the thing that makes LC-ADC beneficial is actually the same thing that makes its limitation. So it's not very good for signals or inputs that are slow and too small input changes. It turns out, because you have to spend a lot of power just to detect that fine changes. Turns out, the neurons have figured it out. Instead of a fixed threshold, like the one you see in the middle, their solution is to do an exponentially decaying threshold. Then, in that way, sometime in the future, you're still gonna guaranteed that there will be an output. There will be a level crossing in the future. So that breaks your trade-off between encoding fidelity and power efficiency. Very nice. Spike encoding also enables this other thing called spike-based processing, specifically with spiking neural networks. Coincidentally, what brains are functionally. So learning-based approaches are inherently robust to read out circuit non-idealities, noise mismatch, whatever. And, it turns out that you need a very ridiculously large noise or mismatch just to get a clear drop-off in your classification accuracy, or it's just basically a measure of how smart your system is. And, perhaps we could relax the readout specifications, and that bodes well for our area and power constraint earlier. This other thing that we're copying from nature is this thing called high spatial resolution sampling. Excuse me. I think we can see very clearly on the examples there that if you reduce the pitch to 25 microns, you can clearly see the fine spatial details encoded in the signal, whereas compared to something that are probably more coarse, then the question is, how fine should we sense? We modeled that, and we saw that maybe a good ballpark number to set is around 200 to 400 microns of pitch. The next thing we found out is you need around 200 sensors to get, sort of a stable classification accuracy. It sort of flatten out and when you try to increase. Okay, now we're done with the bio-inspired approach, we go into the fully integrated solutions. Just because before we go into the details, I'm just gonna say to you that these two chips exactly addressed the two key missing requirements in biological skins I just mentioned. First, with the intuitive chip, it performs the texture sensing on a CMOS chip. It has high spatial resolution, and it performs these embedded receptive fields I mentioned earlier. For the dermis chip, this time with the TFT substrate, we have put a normal and shear force sensing array, this time with a large area coverage to perform slip plus detection. I'm gonna tell that more later. So the key innovation first with the intuitive chip is, this is the first demonstration of everything we have discussed so far. The thing that perhaps we could relax the readout and readout constraints and to be able to achieve your targets and the high spatial resolution you need. We were able to put 12 by 16 per taxel spiking readout, and we were the first ones to integrate piezoelectric sensors on a CMOS chip that are commercially fabricated. Turns out we got 200 micron spatial resolution, which, fun fact, we actually beat human skins in terms of the spatial resolution by 2x. Key system innovation here is we transitioned from a frame-based sampling approach or a software-based spiking approach to something that's performed exclusively in hardware. We're also the first one to implement the heminode or the complex receptive field feature found in fingertips. This is how the taxel circuit looks like, and you have 192 of this. So, of course, you need some way to convert the charge of the sensor to a voltage, which then goes to your level crossing sampling channel. Fun fact, we're actually not limited by the area of the readout, but by the area of the sensors, because they cannot make the photolithography, they cannot make the sensors a little bit smaller, so we can put two channels under the same sensor. So we put level crossing sampling channel and a neuromorphic level crossing channel. And the neuromorphic level crossing channel works with current mode, because the exponentially decaying threshold is just easier to implement with a current mode low-pass filter. Also easier if you want to combine signals, exactly what you do for complex receptive fields, basically combining currents. And these two channels communicate with their own per taxel logic, which then communicates with a global address event representation interface, which basically performs very simple tasks, such as arbitrate between spikes that happen at the same time and assign addresses on the taxels so that you know where the spikes are coming from. So all in all, they fit in this thing. All in all, they fit in a 200 by 200 micron footprint. So we did the sensor post-processing at our partner institute, the Fondazione Bruno Kessler in Povo, Italy. It turns out they cannot handle very small chips to deposit the sensor, so we actually had to order full wafers, which is not quite cheap. You can see here in the picture a quadrant of the wafer with the sensors deposited. In the middle figure, you can see cross-sectional image of the chip with the scanning electron microscope, and you can see clearly the sensor structure on top of the CMOS chip. And side note, connecting the top electrode turns out to be a non-trivial task, which is something we improved on later designs. So key measurement results here, we achieved excellent classification accuracies despite less than 5 bits of resolution, sub-Nyquist sampling, and that allows us to only have a per taxel readout power consumption of 12 nanowatts. Another cool key measurement result here is our proposed neuromorphic way of level crossing sampling actually outperformed the conventional one in terms of the classification accuracy. So, the intuitive chip is very good for texture sensing. But if you want to try another thing, say slip sensing, which is also quite useful, then you have to change quite a lot of the system. First, you have to change the sensors, because now you need sensors that can detect both normal and shear forces, both its static and dynamic components. So we changed from a piezoelectric sensor to a capacitive sensor. We changed our small area coverage to a large area coverage to be able to capture slip. that entailed us to switch from a silicon CMOS design to a thin film transistor implementation. All in all, this captures our dermis implementation. Before I discuss the details of the dermis chip, I'm gonna lay the land for you first. What are the state-of-the-art in tactile sensors that can detect slip? There are a bunch of implementations here, but the key limitation are they have low spatial resolution, so they cannot completely capture the contact. They typically have complex offline slip detection algorithms, therefore they have very large slip detection latency, which is a problem because you want to catch the object slipping before it actually falls. Our dermis vision is to transition from something similar to a fully integrated approach in a thin film technology. But this time with the benefits of high spatial resolution sampling, event-based sensing, and putting some form of intelligence there. It's an end-to-end integration on thin film technology. What are our other options if we want to go large area? People have tried implementing something on exotic substrates. Turns out you really cannot put something meaningful yet with these substrates. They have very coarse integration, limited or no PDK tools, yield issues, so it's very hard to design in this process at the moment. What we did is we chose a commercial fab, which is a Pragmatics IXO TFT. It's dense enough for TFT standards, but it has its limitations. It only has NMOS at the moment. The minimum feature size is 0.6 microns, so you get big digital areas. Flicker noise and the gate source capacitance tend to be bigger because of how the transistors are actually constructed. Some practical limitations: no diodes, no standard DSD cells, no standard digital cells, whole bunch of other things. But that didn't stop us from implementing something meaningful. First, with the sensors. So these address two key limitations with prior designs. First, the top electrode problem I just mentioned earlier. So this time, we made the floating electrode actually floating. Then you ask, where is the capacitive structure if you have a floating top electrode? We actually, found a solution. So the capacitive structure actually goes from the bottom electrode to the top electrode and going back to the bottom electrode. Exactly what you see here in this schematic. It also addressed this other key limitation wherein prior tactile sensors can only detect either shear or normal forces, not both. We can do that here. And you can do that by just simple arithmetic. You can get the normal force just by adding the two sides of the capacitive sensor. You can get the shear force by getting the difference and you divide by the sum. Since we have full control of the system, we tailored our readout to take advantage of this very cool thing. We embed the arithmetic in the readout because turns out digital is very expensive in DFT. Trust me. So we do the sum of the capacitive sensors, very easy for differential structures. You just flip the face of one of your input, and you get the sum. If you want to get the difference, you have two in-phase input here in the middle picture. But doing the division is a little bit more complex. So what we did is we used the neighbor taxel to generate the denominator, and we did a ratiometric design. And that's perfectly, signified by the figure at the bottom. Say your main channel is 3 times bigger than the neighbor, it will cross this neighbor threshold 3 times, then you get 3 spikes. You just did the division you need. So, it turns out, both the normal and shear forces can actually tell you a whole lot of other stuff depending on the current grasp state. So when, say you just touched an object, it can tell you about the friction just by the shear force, the lift off, and the contact. These circuits look very simple, but it's not actually trivial to implement on TFT. For one, a good example is because there are no NMOS in this process, so you have to do a little bit more. So, since you don't have a PMOS, you don't get the large R out of your PMOS. What you do now is you use positive feedback to cancel the GN component of your load NMOS, and then you get again just the R out as your load, which is perfectly captured by the equation here. Another key thing we implemented is, because again with the limitation with the lack of PMOS, normally the output DC of your first stage is very high, whereas perhaps you need your DC of the next stage to be quite low. So a solution there is to basically filter out the DC and put your own DC. But follow the theoretical output very well. The one to the right is the output spectrum of an ADC. Get very decent results considering TFT standards, 6.16 bits. Some tables comparing our work with prior TFT-based designs. Just focus on the bottom. We achieved a 400x smaller AFE area and 17x smaller ADC, 60x lower AFE power consumption. Also, we're only the ones that's doing only everything in TFT. Most prior implementations combine both CMOS and TFT, and we were able to get comparable Walden figure of merit. Combining the two chips, the intuitive chip and the Dermis chip, yields us a solution that is multimodal. Multimodal because we're combining sensors that can sense different modalities. Multi-scale, one is focused on small area localized sensing, one is more focused on large area sensing, and they both perform local processing. These are the three fundamental properties of human skins. We were able to close the gap between e-skin systems and the human skin. This plot shows you all the prior state-of-the-art work in readout designs for e-skin, plot in both the power per taxel and the area per taxel. And the red area there is where you want to be, because that's where we estimate the capabilities of human skin lies. We were able to narrow down the gap from prior 50x to 6x in terms of the power consumption. In terms of exclusively large area designs, 200x to 1.3x. I conclude by saying our methodology was a pragmatic, technology-aware, bio-inspired approach with full control from end to end, where we leverage spike encoding and SNN-based processing. We leverage VLSI in per-taxel readout and sensor miniaturization and integration. Our intuitive chip was the first chip to integrate high spatial resolution on a CMOS chip with complex receptive fields. Our Dermis chip extends the intuitive chip to achieve multimodal and multi-scale system on a TFT substrate. Final takeaway for you: we did everything in a consistent design manner. We decided first what we want to sense, what are the requirements there based on biology. We designed transducers that can capture what we want. We designed the readout to take advantage of the sensors, and we build processing that can actually take advantage of the very crucial information you're capturing across two different substrates, CMOS and TFT. Something to look forward to. Turns out our work is going to be published in a book in the near future. Thank you very much for listening to my presentation.
Thank you very much for a nice survey of your work. But I think now we need some bio-inspired chips that do audio and things like that. Could you switch to that microphone? This one.
Oh yeah.
I introduce the jury members, and as I promised, not everybody is visible here, but there are two jury members online that hopefully you can make visible. This is not a general. There they are. So that's Professor Chiara Bartolozzi. She is from the Istituto Italiano di Tecnologia in Genova. That's obviously in Italy. And also Moshe Kaboli, who is from the Eindhoven University of Technology, that's in the Netherlands. So they will be the first to ask questions, and then we move to the local people here. That's Chris Mini from the Faculty of Engineering Technology, Department of Electrical Engineering, and then I think the other members are all from the faculty of the local faculty of the Department of Electrical Engineering. So that's Michael Kraft, who is sitting here in the row, and then Wim de Hane, who is next to the supervisor. That's George Hille, all from the department, the local department where we are at the moment. My name is Ademar Gauthier. I'm from the Department of Computer Science, but I was asked by the faculty not to be an expert in the subject, but I just look after the more formal aspects. So we will start with Professor Chiara Bartolozzi. Can you please open the discussion?
So the question was, if you have the resources, where would you put it to improve the e-skin design? Is it the sensors or the electronics? I think my answer there, I think, would sort of follow along the steps of my presentation was, which is to treat everything end to end. So perhaps don't focus on one small thing. If you can maybe co-optimize the whole thing, then you get improvement in one can help in improvement in another. Yeah, I hope I satisfied your question, Gary. Okay. Yeah. Yeah, I think now, I think you can sort of divide the answer into two different things. So one is more immediate, something you can do in the immediate future, and the one more, I think, more long term. So the one we can do in the immediate future, chips are normally not trivial to package. And when you're packaging something that would be exposed to mechanical contact, that can be an issue. I think with our thin film approach, we developed a way such that we can just connect the thin film chip into a like a flat cable. You bond it with a conductive glue, and you remove all the bond wires that could be a problem when you're exposing the chip to some mechanical contact. So in the immediate future, I think the most pressing concern is, how do you package, how do you protect your chips from the mechanical contact while preserving the amount of information you're still gonna get. I think with so many things to address. At the top of my mind, perhaps people can look further into this thing where you can relax your readout specs because, spiky neural networks are getting better. Perhaps they could tolerate more noise, more mismatch, more non-idealities. Perhaps you could do something much more simpler than actually what I did, and still, because we managed to narrow the gap of power from 50x to 6x, but 6x is something very close. Perhaps if you could go to the same path as we did, perhaps that could solve the 6x limitation. That's one thing that I can think of at the time. Of course, with implementing something in large area substrates, first with the actual substrate itself, I think with pragmatic IXO, they're starting to put now PMOS, if I'm correct. So that certainly helps a lot because now you can reduce the area, you can reduce the complexity you need, then you can further narrow down the gap. So I think that's also something that you need to address everything in an end-to-end manner, not just one specific thing only. I hope I answered your question, Kara.
Yeah. I have another little one, and then I'll give the stage to Morgan. You spoke about the fact that we have non-idealities in circuits, right? We have noise, we have mismatch. Additionally to this, in tactile, we also have the scarcity of the material, right? So usually, you were talking about that. So you usually cover your sensors with soft things, the dielectric of your capacitors have hysteresis. Will your circuits that you design be robust to the hysteresis of materials? Like I'm thinking about the adaptation of the electric readout circuit where you were adapting the pressures of the neuron. Would that be helpful in coping with the hysteresis of the materials in tactile sensing?
Yeah, I think this question is actually very related to work my colleague is doing that is an expert on sensors. If I remember it right, so now the approach there is to try and play around with the dielectric material to sort of reduce the hysteresis there. And I think putting in microstructures actually would help in terms of solving the hysteresis problem. But unfortunately, I don't know a lot to answer, very comprehensive. But I would sort of maybe, so we address noise and mismatch, but hysteresis no. But I think hysteresis is, something that's also captured with the temporal dynamics of your spike. So say there's some delay in returning to the original value. And I don't know exactly, but I hope still with spiking neural networks, you can still sort of compensate for that behavior. Because the hope there is, tactile perception in biological systems seem to tolerate those things. So maybe going the same direction of leveraging the learning-based approach with spiking neural networks can also solve the same problem.
Okay, thanks a lot. I guess now I
Thank you, Kiara.
Thank you. Maybe we try to put this, bring this in somewhere. Maybe it will work. Okay, yeah, well, sorry, we were trying to get you audible here in the room, but it's still a problem. But maybe you can, well, we will try to fix it first. Just a minute.
Yes,
speaker.
yes, speaker.
Nearby.
Yes, yes, yes.
Okay. Okay. Yeah, okay, now we hear you. Please go ahead.
Thank you.
So you can hear me, right?
Yeah,
Yes.
perfect.
Yeah. Mark, thank you very much for the nice presentation, and it was really great as Kiara mentioned. I liked especially the motivation part, the part you were talking about. Why do we need and what are the applications? And also some nice demos of from the robots that are failing. So I really appreciate what you have done, and I think I have already mentioned to you even in several occasions. I think I believe that the sensor you have developed, especially intuitive, I think has the highest spatial resolution, and I think I haven't seen before, and this is very great. I think this is for me to my knowledge is the only word at the moment. I think maybe the first word with this number of resolution. So for me, maybe the question comes: what are the challenges you see if you want to, for example, cover one hand or a whole body of the robot with the sensors, right? So as you basically you mentioned, of course we needed the tactile sensing for object recognition, but there is other main application which is the body perception, and also which is very basically is very important, especially when it comes to the humanoid. And then you were basically showing some of the failures where the humanoid was not able to properly walk, or when it comes to the interaction, whole body interaction, couldn't feel the body of the basically the humans. Means there was one example, the robot was going back and couldn't see, but when it comes to the human, we can feel it. So if I want to summarize it and to again come with to the question, what are the challenges going from fingertip to the entire hand, and later on the whole body tactile sensing?
Yeah, that's actually one of the slides I deleted because, working with chips, you tend to have limitations. One major limitation is the size, of course. And we try to, make the area a little bit bigger with thin film technology, but some, there would be still a limitation with the wafer size and all. So one slide I actually put in the presentation is, of course, large area coverage in the body with chips is probably not practical. So this is exactly the reason why we focused on the fingertips, because then you can focus on small localized area, then where you can leverage the amazing progress of VLSI, because there you can put the high spatial resolution stuff, the power efficient stuff, and the processing whatever. And I think, with chips, it's probably difficult to do large area, body area coverage. But I've seen recently people, starting to do this with, so basically they're putting sensors and they're putting some electronics and an antenna. So they're basically building a body area network. So it's, you know, it's a promising step towards addressing whole body coverage, but you also tend to have some limitations there. For one, power could be an issue because then you have to transmit, and if you don't do the data compression, you're sending a lot of data there, and if you combine a whole, you know, to cover the body, then, I don't know, it could be hard for your receiver somewhere to, you know, arbitrate all the inputs. I think that's a promising step, but, you know, it has still its limitations. You could also do this with the, so we also were planning at some point to tile in multiple chips to form a larger network in the hand. I think we actually built PCBs for that. It's just we didn't have the time to do it eventually, but it's also something we were planning at some point. Mohsen, I hope I answered your question.
Yeah, thank you very much. Maybe the last question I have. So since you are basically now expert, as even Chiara mentioned, in the field of the basically designing a tactile on chip. So if you basically you explain the human's sense of touch, and human sense of touch is a multimodal, meaning that we can feel normal force and shear force, and beside that also the temperature, even the humidity, and there are other factors as well. Do you think there is a possibility even to integrate kind of, let's say, other sensors, like a thermometer, you know, or to measure the humidity and so on, in a chip to have to create like a multimodal, even, you know, in one small chip as a basically like one multimodal chip receptors, something like that. There is a possibility, or maybe we have to have kind of a distributed sensors within the finger or hand or body.
Actually, I'm gonna go and find the slide here somewhere. I'm gonna share again the screen so Mohsen, we can see you.
Yes, I can see.
Oh.
Yeah, I can see.
Okay. So actually, the intuitive chip has a temperature sensor somewhere. There on the lower right corner there. We didn't use it for tactile classification experiments. I did use it to monitor my chip. If, you know, something's going bad, oh, maybe the chip is very hot. But we didn't use it for tactile experiments. Perhaps we could also use this output to improve the accuracy of the classification. But this temperature sensor is not spike-based, so it's basically a PTAT generator. So you still have to convert to spikes if you want to use spike neural network. But as you said, we did consider, you know, because we know that human skin sensing is multimodal, so we put in a temperature sensor there.
I think most probably there would be a possibility because next to the texture, as you mentioned, can be used for the material detection. For example, when it comes to metal, usually metal, you know, is colder than like the wood or, you know, beside the texture. Yeah, thank you very much, Mark. I think I'm happy with the answer. Yeah, and then now over to the chair.
Thank you, Mohsen.
Thank you very much. So we move to the local people, Professor Mini.
Oh, thank you. Yeah, I was actually, I liked that one video with the woman with the feedback on her breast, and but of course the unnatural movement of the hands. It was unexpected, but okay. But then this showed us what actually is the direction, because in the end you have I can think about the pragmatic chip on every finger connected to a silicon chip somewhere on the hand or on the palm, which then communicates on the rest. But in the end, that was not what was made now, because now you focused on the derms and the intuitive chip separately. But I was wondering, let's start with the dermis chip. Well, there was a statement of you that digital is, I don't know what was written on the slide, but you cannot trust the digital somehow. And I saw the power numbers, 50 milliwatt. Okay, I understand that from your perspective, but nowadays we do better. Yeah, expensive, but only in power, not in area.
In power,
yeah, okay.
Somehow also in area just because of the feature size, but when you compare it to CMOS, of course.
Yeah, because there I was wondering, the digital is one of the first things that moves to silicon.
Yes,
I guess. But how does it then work with the spikes that you generate in the pixel or in the taxo? Because that still goes on the common line.
Yes.
So how do you see that then?
Yeah, I actually thought of this question. So we saw that digital is power expensive, area-wise also.
Yeah.
But the good thing with this address event representation interface is before the actual digital, it's just a simple, pull down logic. And all rows would pull down to request, all columns would pull down. And if you want to, put the digital off chip or off TFT, perhaps we could just send out this, this long pull down line and connect it individually per row to a CMOS chip. Then you put the digital there.
Maybe that could work. But then, in order to solve the digital, I was thinking you have spikes. Mm-hmm. Is there no way that we can think about asynchronous digital logic with dynamic? Because in the end, that would also lower the power.
So the address event representation interface is indeed asynchronous at its current form.
But you don't use it.
You didn't use the I think you're referring to like a library that's a dynamic library. Yeah, I think I would say the practical answer there is we were building stuff in TFT. We didn't know, the risks. So we sort of settled with something maybe more mature and something that's available, and that we can use all the synthesis and place and route tools and implement something in a reasonable amount of time. But of course, if we can use standard tools to implement it, then it's more or less plug and play, I would say.
Yes. And the ADC in the TFT which you made, there I was wondering, you selected a certain number of bits, but in the previous, one of the former slides you showed that actually the resolution is not that important. So there I was wondering, why did you select this one, and what if you would make it smaller, the resolution smaller, because then you can gain area and speed and whatever. So
True. Yeah. So first of all, the ADC in the intuitive chip and the ADC in the dermis chip, it's the same architecture. It's the same level crossing ADC architecture.
But not the same resolution.
Not the same resolution, indeed. Yes. Indeed, you can sort of maybe lower the resolution with the dermis chip. I think, again, the practical answer there is you don't really know how much you can push down in terms of relaxing the readout specs until you don't get anything meaningful out of it. I don't know exactly, I don't remember exactly, how I decided to, settle down with this resolution, but it follows along the lines, try and design something that works. And in terms of the power consumption, it's also not super bad. So
that was not bad. I was just thinking, if we have to optimize, if we make it smaller and put less transistors in the pixels, because that's the goal for TFTs.
Yeah. So actually, a lot of the power there is mainly with the static leakage of the digital.
Yeah, but I'm excluding the digital because we solved it a few minutes ago.
Yeah, but So, well, this one with the ADC, I actually used a slightly different architecture. I used differential logic. So, because I chose that because I know this other architecture could have a larger power consumption. So I sort of made everything by hand actually because it's just 10 gates in total. So if you don't consider the digital, I think a lot of the what they call this, the overhead with the design, say for example, is basically your inability to use a PMOS. For example, you need the positive feedback thing, that's additional amplifier to set the feedback. You don't have a PMOS, so you would put a resistive load for your gain stage, and you cannot increase so much the resistor without getting a large area. So I think if PMOS comes in the near future, I think that solves a lot of the issues, I would say.
Okay, let's hope. Okay, then one final question for me, to also put the intuitive chip a bit under the attention, because you also worked on that. Yeah, there I'm more a bit. You have this V-common mode, which is used, but I guess it also routed over the top metal, which is, well, I saw in your thesis the 3D cross section. So I was wondering how much does the resistance of the top layer plays a role in the V-common mode then, and how much will it affect your performance?
Yeah. So let me find the slide that shows that. I also put in the slides there that connecting the top electrode you just deposited on your CMOS chip to a non-potential turns out not to be a trivial task. We found a way to, manually put in an epoxy, connect the, we put in an area wherein the deposited top electrode and, 8x2 pads, normal CMOS pads, they have some overlap area, and then we can just drop a conductive glue there and we can connect them. You can connect the internal connection of the chip to a known bond pad. We didn't characterize the resistance, but the thing for here is, I think just the dielectric enough has so much more parasitic resistance than that top electrode connection. Okay. It's still a basically a capacitor, so it's only leakage that's flowing on the PCF electric sensor. I don't think that would be an issue. Yeah.
Okay. Thank you.
Yeah, thank you. Well, thesis, very nice presentation. I like your approach of explaining really something to the general public as well. It's really well done. Actually, it triggered my first question, actually, seeing the videos. So I think the two primary applications of your work would be in robotics, indeed, and in human prosthesis integration. But I would argue that the specifications for these two main applications are quite different. So could you comment on that, maybe?
In what way are they different?
Yeah, well, that's my question. How do you? I mean, I sort of intuitively think that they are different.
Yeah.
If you put your chips on a, let's say, on a robot, as well integrated in a human prosthesis, right? So I wonder how you would go about defining these specifications and how you could actually derive them.
Okay. Yeah. Well, I think first of all, the idea of using chips for tactile sensing is probably not a wild idea in the first place. I think groups from Singapore, they're using chips as well, but they don't use the commercial CMOS fabs we use, so they typically have lower spatial resolution. I think the practical issue there again is so you have a very nice chip, but then you still have to connect something out because you have to read out its output, and that's probably not easy because chips are normally connected with bond wires, and this can get damaged, as I've seen, of course, with my mechanical, mechanical experiments. To solve that problem, you can approach it in two ways. So one is practical engineering. Find a way to protect the bond wires. Like I said, in the thin film technology, maybe you can glue a flat cable, and that's pretty much very robust. And you can solve it with putting in more intelligence on the chip. In that way, instead of sending maybe, 5 bits of data, you can send a binary signal. Okay, there's a slip, there is no slip. So that saves you practically the number of connections you're gonna need. And that's when you're trying to solve, I really think the most pressing issue with using a chip-based approach.
I was actually aiming more at the differences of your specifications and requirements between these two applications you mentioned, robots, robotic skin, and prothesis. So for prothesis to mimic human touch, you can quantify this quite easily, right? Because there are surely biological experiments that and literature that tells you what is actually the minimum slip force a human hand can feel, or the maximum pressure it can withstand, and these sort of numbers, right? So have you looked into that?
Yes.
Have you derived specifications from the human touch?
So I don't remember the exact numbers, but I did just quite that. So the key there is you find neuroscience papers that deal with this. I think the number is some order of 5 newtons. That's the maximum everyday amount of force that's in contact with the finger.
Mm-hmm.
And there's also a paper that suggests this could be the absolute maximum, which is around, I think, 17 newtons or something.
Yeah.
And this is when you're trying to damage the finger.
Yeah, exactly.
Yeah.
There's a maximum where you damage your
Yeah.
finger if you hit with a hammer and
Exactly.
on the finger and not on the nail, for example.
Yes.
But how does that now translate into your chip?
Ah.
This number here. Pi for 17 Newton or whatever it is. Yeah.
So not sure on the actual maximum value, but I'm more sure with the minimum value.
Okay.
So I think the minimum value is something in the order of, I don't know if it's 5 millinewtons. And it's done with experiments of like fine touch. They basically stroke the fingertip and see how much force you need to apply to get one spike.
Yeah.
I think 5 millinewtons.
Yeah.
With regards to the dermis system, you can sort of get the absolute minimum resolution you can get by sort of converting basically the voltage noise input referred. You change it to capacitance referred resolution. Then I think we're getting around 2 millinewton RMS of force resolution when you convert the voltage noise to something that's force related.
Okay.
So that's for voltage noise.
Yeah. So my second question is maybe a little bit provocative in the sense of you said a lot of limitations and problems with the TFT approach. Yeah? Digital is expensive. The area is limited with your chip. There were quite a few electronic limitations, right, with the TFT. Now, this led me to the thought of, is this actually using TFT the right approach in the first place? Because the other approach could be that I have a flexible and stretchable substrate where I have my digitalized sensing element itself, which also can be made out of polymers and flexible and stretchable and so on. And then I have interconnects that lead to very small but standard CMOS processors, which are cheap and cheerful. There's no limitations of what you have with the TFT, at least what you outlined here, right? So, can you comment on this? Where do I go wrong thinking that this would be the better approach?
Yeah, I see what you're getting at. So, yeah, in fact, I think a lot of the the EMG, the ECG applications, they perform their amplifier, LNA in the TFT, then they perform the analog to digital conversion on CMOS chip. I think the problem there is, so if you put all the sensors, perhaps maybe an amplifier on TFT, then you go back to the problem that you have to physically connect all the voltage output, you get a lot of the wires back again, just to connect it physically to the CMOS chip, which is again a problem that it's an engineering problem, but it's actually real practical problem that people need to address. So,
you what you're saying is mainly an interconnect problem.
Interconnect problem, yes.
There are, of course, a lot of interesting approaches to solve that as well, and it would solve your area limitation to some extent. Okay. Anyway, I still like your work.
Thank you.
Thank you. Thank you.
Thank you,
Indeed, a very entertaining and even humorous presentation. I appreciate that you don't disconnect before we have asked our questions. I was going to ask about this CMOS and TFT combinations also, but it's been addressed by my colleagues, and I fully agree that the combination could be optimized. I have one question left. You use this whole, how should I call this, event-based, non-uniform sampling thing, which is a research strategy, that's fine. Yet also after that, processing becomes much more complicated. You probably didn't study that, but at the end of a PhD you have to think wider. What if we would have just put a normal, good old SAR or whatever type of A-to-D converter and then do some digital processing as we, not on the TFT, but as we're used to? Would that be so much worse or after all? In performance, in power, I leave it up to you.
I think just for the first part of the question is about okay, so you're converting everything in spikes, but then you have to process the spikes. I think that's like one big problem with these things. You save a lot of power with the ADC, but then reconstructing the signal, you need very fast, high-speed clocks to still get the resolution.
Which is definitely not TFT compatible.
Yes,
I agree with that.
So that problem is actually solved by using another form of processing, using spike and neural network. You don't have to reconstruct, feed directly your spikes. The question about using SAR and maybe using a digital to do the compression. I mean, I think at some point I thought about that. Let me remember.
All right.
I think that's sort of what people are doing now, because they're sampling everything with the conventional frame-based ADC, and then they do the software-based approach, but this time for you it's a completely digital accelerator thing. But I think the key point there is, perhaps if you still want to do per taxel readout, I don't know how much digital you might want to put per taxel, because maybe if you scale to like 500 sensors, then that's a big digital to process everything all at once, and cannot underestimate digital, of course, as you know. It can be problematic.
Yeah, but it can also consume a lot of power.
Yes, so it's a good idea, but I'm not sure how much overhead you're gonna put now on the digital. You saved a lot of power with the SAR, but I don't know with the digital.
I think it was back to what Chris was asking, how efficient you can make the interface, because the interface between TFT and digital, you can also not have infinitely large bandwidth, and if you do everything there, okay, let's stop here and pass the word.
Thank you.
Set of questions. No, I as a last person, I can only iterate on what others have been asking before. You showed Moore's law.
Mm-hmm.
There is certainly also a Moore's law for TFT.
Mm-hmm.
They are even talking about this year taking into commercial production the fact that they have complementary devices, PMOS and NMOS both on this year commercially available, and the downscaling will also happen in the near future.
Yeah.
So that being said, if we look 4 years or 5, 6 years ahead, and there's a Moore's law for TFT technology with complementary devices, what would then be the partitioning that you would suggest? Would we put everything from the dermis chip back into digital and put it on the TFT? Or would we keep it with your current dermis solution? What would you suggest?
So, by Moore's law scaling in TFT, I assume you're sort of addressing all the digital problems I sort of had.
Exactly.
So, then I'm going to show us a slide actually. So you can see from the breakdown there, is the yellow part is just the digital, so it's very bad. And with this, so this is AER interface. And if you do the Moore's law and everything scales back, then you solve a big chunk of the problem with the TFT approach. And not only that, perhaps you can put more intelligence in your TFT chip. For now, there's a simple state machine included on the power consumption of the digital there somewhere that just basically tracks where the grasp state is at the moment. So are you about to touch an object? Are you in the manipulation state? Then you know if the shear force is friction, if the shear force is lift off. If you get ambitious, if you get digital power that's cheap, then you can put in more stuff like this. People have, I think, started to put spiking neural networks on TFT. That's also something we could explore. Because that solves your problem of your output bandwidth, but also physical connections, because you're sort of compressing a lot of the information that's getting out. I hope you answered your question, George.
Yeah, so the answer is we hope that this Moore's law for TFT is going on. And then, Now the second and last question is the philosophical one from which you started, neuromorphic versus bio-inspired.
Okay.
You say that you're not doing neuromorphic, but you're doing bio-inspired.
Yes.
But if I look at your circuits, it pretty much looks like neuromorphic.
Yeah, no,
So in what sense is your bio-inspired not neuromorphic?
So, well, I think for my own definition, neuromorphic and bio-inspired are the same. So I'm doing both. What I'm not doing is copying blindly biology.
Yeah, so that was my question.
Yeah.
In what sense are you not copying biology?
Yes, so...
Because you have your senses, they come together, Merkel cells and so on, and that's exactly what our human skin is doing.
So, the quick answer to that is in terms of how I convert the sensor signal to spikes. I think most neuromorphic approach, they put in a lot of the complexity to try and faithfully replicate how a neurons would fire. So, instead of one exponentially decaying filter, you get 10 of those just to match what is recorded from neuroscience. And those are not, something that's cheap to implement power-wise. It's gonna drain, even microamps of current just because everything works in current mode. I have a slide actually. So I think what I did with the dissertation is I sort of first relate how a neuron and an LCADC differs and what's the similarity there. And I sort of, summarized it in this figure. So I think that the key thing with neuromorphic LCADC design is you're getting the event-based conversion. Neurons, if you replicate the slowly adaptive kind, it's not purely event-based. It will continually fire when there's input. And that would consume a lot of power for you system-wise. Here, we didn't copy that. We still, from the perspective of electronics, try and meet with the neuromorphic people. What is a good compromise here? We don't want all the complexity of a neuron. This is simple enough and it works. So I think that's how I would approach it.
Okay, so the engineering pick and place methodology to get to it.
Yes.
Yeah. Okay, thank you.
Thank you, George.
Potentially the last question, it was not the last. I have to invite questions from the public. Anybody? No question? Okay, in that case the jury will have a short deliberation. We will be back in a few minutes. So Michelle and Chiara, please move to the other meeting. We will be switching on as soon as we arrive there. Geachte collega's, dear colleagues. I have the honor to inform you of the outcome of the deliberation of the examination committee that is appointed for the examination for the degree of Doctor of Engineering Science. Mark Daniel Alea has submitted a thesis to the faculty that is entitled Chips That Feel, Fully Integrated Bio-inspired Electronic Skin Systems. And this is in order to obtain the degree of Doctor of Engineering Science. And he has defended his thesis in a public session before the examination committee. Dutch is still the official language of our university, so to make it official, I read something in Dutch as well. Ik geef u kennis van de uitslag van de beraadslaging van de examencommissie die is aangesteld voor de proef van dokter in de ingenieurswetenschappen. Mark Daniel Alea heeft aan de faculteit een proefschrift voorgelegd dat is getiteld Chips die voelen, volledig geïntegreerde bio-geïnspireerde elektronische huidsystemen. En dit tot het verkrijgen van de graad van dokter in de ingenieurswetenschappen. En heeft dit proefschrift in een openbare zitting voor de examencommissie verdedigd. De examencommissie heeft op 22 januari 2026 vastgesteld dat zowel aan de wettelijke en decretale bepalingen als aan de voorschriften van het universiteitsreglement ter zake werd voldaan. Dear Mark Daniel Alea, the examination board has determined that you have met all the requirements prescribed by the law and by the university regulations for the doctoral examination. Therefore, and on behalf of the Rector of the KU Leuven, I confer upon you the degree of Doctor of Engineering Science in Electrical Engineering, but again, in accordance with legal provisions, I also make this announcement in Dutch. So this is the magic formula that makes it happen. Bijgevolg en in naam van de rector van de KU Leuven verleen ik u de graad van dokter in de ingenieurswetenschappen richting elektrotechniek. Congratulations. So this ends the official part. You may all sit down. We can take off our hats. By obtaining the doctoral degree, you commit to act in accordance with the basic principles of research integrity as described in the All European Academy's European Code of Conduct. That implies reliability, honesty, respect, and accountability. So I hope you agree with that. I leave the floor to the supervisor who wants to say a few words to the new doctor. So please.
Okay, I won't take too much time. Dr. Mark, as you can see, Mark Alea, he's from France. You see him dressed all in blue. No, you're confused, he's from the Philippines. And he's very proud to be a Filipino. And I think you're the first Filipino to get a PhD in my class. There are a few who were on the way before him, but who, for some reason, get delayed. But I'm very pleased to have Mark. Back in 2019, we had a ITN, European Training Network project, applied, and then it got accepted, and then I made a vacancy for a PhD position, and then we have lots of candidates, and out of those candidates, in beginning of 2020, I chose Mark. His CV kind of struck me, and then I picked him, and he accepted the invitation, and he decided to apply for it, and I selected him, and that was 2020, beginning of 2020. Now you know what happened in 2020, that was COVID, so he got accepted, but it took a while for him to get here. He even was one of the first to start working on the PhD while still being in the Philippines. Because we had the contract, everything was set up, only he couldn't get the visa at that moment. But fortunately, a few months later, he did manage to get here. And since then, we are working on this wonderful project to have people with prosthetic arms feel and sense the same way as humans do, even if they lost their arm later on. And so we focused on trying to solve that problem technologically, and so Mark did. And he said, okay, with chips I can do it, and we can do it better than humans. But then we found that chips also have their limitations, and then we went to the second solution, the Dermis project, where we try to have a larger area than you can have with chips. And that we did since 2020 until now. And as you can see, he is dressed up as a Filipino today, but he has adapted quite a lot to the European standards. He's drinking well, and I can already predict that we'll have a nice foamy reception. And for those of you who know Mark, he can also play a nice piece of music. I don't know if he brought his guitar today, but he would really be a good player if somebody else can sing for him. But I'm very glad that we brought this to an end, that we had two engineering solutions for this e-skin problem. And I think it will continue, technology will further develop, other people will continue in that line, And very soon we will have really prosthetic or robotic arms that have the same touch capabilities as humans. And Mark, you can be proud that you contributed to that. Thank you. And congratulations for the next part of your life here in Belgium.
Thank you.
Yeah. Thank you.
I'm just gonna give the jury a little bit of something from the Philippines. So these are models of a jeepney. It's our form of transportation in the Philippines. So something to just, yes. Thank you. That's it. Of course.
I'm glad it's not a balloon.
It will come soon. I prepared something of a speech, maybe a little bit long, so bear with me. It's so fascinating how people can be overwhelmed by so many things and hyper-focus on what we want to achieve at a given time, and then so quickly forget the duress we just went through once everything is said and done. And honestly, that's probably a good thing, because it means we get to move on and make room for the next challenge. In the end, maybe no one cares that much about your work during your PhD, but at least you get to meet and know so many good people along the way. My PhD, as thousands of other unfortunate graduate student souls have complained, has not been smooth sailing. I did achieve a lot of things that younger me would not have dreamt of, but I also fell short in so many things I wanted to achieve that sometimes I just contemplate whether I am lazy or over-ambitious. I am notoriously very harsh on myself. That explains why for long periods in my PhD I was not sleeping, sometimes crying. Why is this piece of crap calcium-based neural network not working? Why is this simulation not converging? I was basically surviving on caffeine. In fact, I was drinking more than 10 cups of coffee per day at some point, and then we realized we bought the uncaffeinated kind. For a long time, for me, starting a PhD was just one of those things you wanted to take a stab at, but you couldn't muster enough courage and effort to actually do it. Like learning how to play the saxophone, or maybe one day getting back to Brazilian Jiu-Jitsu. But hey, eventually we did it, and congratulations to yourself. First of all, I want to thank my wife, Charmaine. Charmaine, thank you for being the one consistent in my life. Thank you for tolerating my bad days, for listening always, and for believing in me even when things were uncertain. Thank you for sacrificing so much, your work and the life you built in the Philippines, so we could take on this Belgium adventure together. Most of all, thank you for your trust, for trusting that we could survive during the times when you basically had to give up your job. I'm incredibly proud of you for finishing your master's. You became a Leuven alumna faster than me. I saw all your struggles, just as you've seen mine. We've been strengthened not only by time, but by love. And I'm excited for the next phase of our lives. To my family, thank you. Thank you for the guidance, the trust, and the steady support that brought me here. And even if you can't attend my defense, I want you to know this achievement is for all of us. I share it with you. I want to thank my supervisor, George. Moving to a different country, interacting with people I didn't know, and navigating different cultures were not easy. I had to learn on the fly. Navigating a supervisor-student relationship in the West, sadly, is not something I'd been briefed on beforehand. Maybe it was the cultural differences, or the age gap, or both. In fact, it took me about 2 years to drop the professor and just call you George. We've always had a lot of friendly chat in the office, and then when I get home, I'd received an email when I get back and say, wait a minute, what the freak did I do to George? I appreciate the opportunity to work together and what I learned along the way. We have so much in common. We want to push people to achieve their true potential, and we also send late night emails on Sundays. I must say, as cliche as it sounds, I would not have done most of this without your eager but subtle pressure. George, as you approach your last days as a professor, I sincerely hope you enjoy your retirement and fix your sleep schedule. Thanks for helping me make the move to Belgium for me and my wife. I would like to thank Professor Ademar Bothe committee. My PhD would not have been as fun, as fruitful as it has been if I had not met the wonderful people of the Intuitive Project. Throughout the various segments of the Intuitive Project, I got to meet so many wonderful people. I'm proud to say that the experts I met are now my friends. To the warmest people in Trento, Italy, thank you for the technical guidance and your friendship. I loved our talks during lunch and our short walks on the hilly parts of Povo. To my fellow Italians and roommates of BO226, thank you for being super warm and accommodating to me. Thank you for taking the time to listen to me complain and rant about stuff. After all, it's super fair because I also had to endure all the long Italian rants from you and the other Italian colleagues in our office, which at some point became the Italian convergence point for some reason. Marco, I enjoyed our technical collaboration and thank you for the carbonara romana recipe. Over the 5 long years, I'm proud to say that our weird humor is now so well aligned that we basically solved racism. My regards to you, Elenia, and especially to little Cecilia. Sergio, thank you as well for the long talks, your technical advice on anything PCBs, and your occasional gifts of pecorino and guanciale. I doubt you will find better office mates than me and Marco, so good luck with the rest of your Liga stay. Tell them not to ask why you cover your monitors and return all the markers to their proper places. Maron! To my Mika's colleagues, past and present, too many to mention, thank you for the many receptions and hallway talks. I appreciate how you all transformed once you had a few beers. I wish you all the best and I hope I helped you in my own little ways. I hope you enjoyed the occasional ubi cakes. I leave it all now to Ryan to continue this tradition. Special mention to Maria, my partner in crime in this tactile sensor work. I literally would not have finished the PhD if not for your sensor fabrication. Thank you for being nice and being a nice and accommodating person in general. Thank you to my Filipino Mika's mates, Rico and Ryan. Thank you for helping me navigate the office and keeping me company. Rico, thank you for informing me about the Leuven opening. Things would have been so different, but maybe a lot more sad if I went through with my original US PhD plan. Without you, we literally would not have survived our first days in Leuven because you bought us our first rice cooker. Imagine life without rice, the horror. To the Mika staff, thank you very much for your support all throughout my PhD. Rudy, Donald, and Frederick, thank you for being so patient with my countless bonding, new instrument, and chip photo requests, and many more. You guys have helped so many people throughout their PhDs that you honestly deserve a meeting room in Mika's named after you. And to the Filipino community in Leuven and Belgium in general, thank you for being a slice of home to this country. I really enjoyed all our Audimat adventures, our potluck and dinners, our barbecues, and so much more. Good luck with finishing your own PhDs as well. If I leave you all with one advice, if your chip is not working, you can always blame the PCB. After that, you can also blame the foundry. And with that, thank you all for being here, for the support, and for pretending to care about my slides. Thank you all, and maraming salamat.